Hi and welcome. I'm trying to learn particle physics. Today, the symmetry of a standard model, and after we've done that, we're going to do ECU tendon training. The ECU tendon is here, and then you participate in the ECU tendon training as well as the owners. Now, it isn't always obvious what is conserved and what isn't. For a long time, it was assumed that mass couldn't be created or destroyed, but Einstein's famous E=mc² said otherwise. Matter can be created, if not out of thin air, then out of pure energy. Although humans are made out of molecules that are made of protons and neutrons, those protons and neutrons are made of quarks. Quarks, as it happens, are so light that they make up only about 1 to 2% of a human's body mass. The rest comes from the incredible energies with which these quarks interact. Although matter can be created from energy, energy itself in all its myriad forms adds up to a constant and permanent total. Before Minerva, energy was simply presumed to be conserved, an assumption so basic that it became known in the 19th century as the first law of thermodynamics. But do the mathematics associated with Minerva's theorem, and it becomes plain that energy is conserved because of an even more basic symmetry. Specifically, that the laws of physics aren't changing with time. If they did, energy wouldn't be conserved. What Minerva's theorem adds up to is a practical prescription for making progress in physics. Identify symmetry in the world's workings, and the associated conservation law will allow you to start meaningful calculations. So people have to find a symmetry somewhere, and then we can start to calculate it out. But it is also, in a sense, a statement about how the universe should be structured. When we look at the universe on the human scale, or even at the level of our solar system, space seems very different from a smooth lake. There are planet-sized bumps and wiggles. Okay, so if you look out there into the space, when there are boogles, and the other thing was planet-sized bumps, wiggles and bumps. But take a broader picture on the scale of hundreds of millions of light years, and the universe appears much smoother. Where are these buggles or whatever, these bumps and these wiggles? Okay, whatever. The assumption is that on the very large scale, the universe is more or less the same. What do I mean with that? As we lack the ability to travel billions of light years to beyond the observable horizon of our most powerful telescopes, this really is just an assumption, and it goes by the name of a cosmological principle. It tells us that what we call down on Earth is nothing more than a consequence of the relative position of us and the rock we're standing on. The universe has no up or down, nor center for that matter. Its laws don't seem to be in any way related to where we measure them, how our measuring devices are pointed, or even when we decide to make the measurements. The physical laws are always the same, everywhere. Is that even true? Through Minerva's theorem, symmetries of space and time yield conservation of energy, momentum, and angular momentum everywhere all the time. Symmetries exist everywhere in nature. Minerva's theorem of 1915 provides a way to translate them into laws useful for calculations. It's translation and time symmetry. The basic laws of physics do not vary over time. Consequence, energy is conserved. However, many times the pendulum swings. With no air resistance, it will always reach the same height. The pendulum will forever swing on if there's no air resistance stopping it, or someone taking it, stopping it. It will forever swing on. Why? Why is the time passing? How can things exist without changing, without altering its state? But there's more. Symmetries in space and time might be obvious to the naked eye, yet Noether's theorem's true strength comes from internal symmetries. To the uninitiated, the standard model of particle physics is nothing more than a list of fundamental forces and principles, but it is a model of internal symmetries writ large, and it was built on Noether's theorem. The most familiar force it deals with its electromagnetism. One of its assumptions of James Clerk Maxwell's unified theory of electromagnetism, formulated in the 1860s, is that electric charge is neither created nor destroyed. That idea goes back even further to Benjamin Franklin in the 1740s. Noether's theorem shows that charge conservation, too, arises from a symmetry. Fundamental particles have a property called spin, and just as position doesn't matter on a frozen lake, what is known as the spin's phase doesn't change physical calculations. Turn every electron in the universe an extra degree and neither energy nor anything else changes. Yes, if you turn an electron around, it's still the same energy. But why does the pendulum keep forever swinging? Why does the pendulum not need energy to swing? How can be something in movement without needing energy? That was Newton's first law, the laws of motion. A thing keeps in motion or standing if a force is acted upon it. Why keeps it moving? If the object moving consists out of fermions and it moves through matter, and that while time is passing, then does that tell us anything about how the matter is constructed? Turn every electron in the universe an extra degree and neither energy nor anything else changes. What pops out according to Noether's mathematics is charge conservation. Hermann Weyl took his idea of phase symmetry a step further and supposed that every electron might be twisted by a different amount and still remain the same. Assume this and almost by magic all four of Maxwell's equations emerge. I don't really have it. As the standard model has developed, so the symmetries of interest have become more subtle. But Noether's theorem has been the gift that keeps on giving. It is hard to conceive, for example, that electrons, the particles that run through wires to power electronics, and neutrinos, which fly through us by the trillions every second without leaving a mark, are in some sense the same particle. Neutrinos primarily interact through the weak force, which controls nuclear fusion in the sun. Now I don't have time yet. If you were here for particle physics, you can go directly to the next part where we will continue with particle physics. Now we're going to do the ECU tendon training. If you participate in the ECU tendon training, then is mit dir auch risk. Going to stand, arms next to us, hands from the fists, and we are doing the floodgate. The fists down, hold it, and then up and hold that. Again down. And up. Again down. And last time. Now we come to a fat money check. And we bring the fists up. And again down. We're having 3 joules. No, first of all, this is all that the owner can participate, but then say. And the 3 joules, the first joule is that we're stopping immediately as soon as there's pain. The second joule is that we're going on as fast as we can go with a little bit of effort. And the third joule is that we're doing it. We just understand from not to exhaust. If you want to take a break, do it. I'm going to use now a tennis racket. A tennis racket is light, just around 300 grams. Does it have? So whatever you use as a dumbbell, do it at your own risk. Do it according to our 3 joules. Have the elbow in, and we're doing a mannequin eagle. Bring the arms slowly over to one side, and back over to the other side. if things in motion stay in motion, or if we're not doing something, doing nothing. Why do then any type of reactions, chemical reactions or whatever, happen in the universe at all? Is not the basic idea that humans can have an influence on an object the proof that this theory is wrong? Because every force by itself is not a force which can only be altered by having a force changing upon it. And because we can prove that we can have an effect on other things, does it not mean that somewhere this is wrong? Or does it mean that we have no free will, that even the slightest thing is already planned in as a force? No, I'm out of the mistake. Why is anything moving at all if things cannot change its altering state? It would mean that things have always moved. Now, what do the people studying the Big Bang say to it? And the answer. Oh, there you are. What's that? Don't bother. Right now we'll harvest the ogre. Take whatever reliquage from the top, lift the arm up, and bring it over. Okay. And down. And another time. And now, with the palm facing upwards, the garbage truck's clever arm. Oh, okay, well. I'm going to use now a sock, but you can also use a t-shirt or whatever. Just press a good force under it and bring the wrist up. And then down. And again up. And again down. Up. also the other side, and now over, again pressing, bring your wrist up, and down, again up, and down, and the last time up. Now I don't have that. So I thank you very much, and until next time.